Good morning class and welcome to another lecture in sustainable energy technology. In the previous class, we were continuing our discussion on wind turbines and we found that the maximum efficiency or power coefficient Cp that a wind turbine can have is given by 0.593, which is the Betz limit. So, of the total wind energy that is available for conversion into mechanical energy of wind turbines, which is half rho A V1 cube, 59.3% can be converted into mechanical power under ideal conditions where we are ignoring frictional losses or any kind of loss related effects. Okay. So this is the ideal limit of power conversion that a wind turbine can achieve. So this ideal limit also kind of constrains the wind turbine designs that are used in modern wind turbines. If you think about it, most modern wind turbines have three blades. So a three-bladed wind turbine. So two blades like this, another blade like this. Okay. Why use this kind of a design? Why not have two blades or four blades or six blades? So the reason is the impact the number of blades has on the maximum possible efficiency for a wind turbine. So here we have a plot for the coefficient of power, the efficiency or coefficient of power Cp value, and what is called the tip speed ratio. This tip speed ratio is the ratio of the tip velocity by the wind velocity. So here the idea is this. Suppose you have a wind turbine blade that is rotating like this. Okay, it has a angular velocity omega, and the tip velocity is the omega into the radius of the blade. So the tangential velocity of the blade at its tip, that is the tip velocity. That is basically the angular velocity omega of the blade into the radius of the blade, which is r. Okay, so that tip velocity by the wind velocity is called the tip speed ratio lambda. Okay, so lambda equals to 10 means the tip velocity is 10 times the wind velocity. Okay, so that's the idea. So clearly the power coefficient or the efficiency depends on the tip speed ratio, and it also depends on the number of blades. This is the ideal Betz limit given a certain tip speed ratio. Okay, and these are various types of wind turbine designs. So this one is a single bladed wind turbine design, so you have one blade only. Okay, the efficiency for this one bladed wind turbine peaks at very high tip speed ratio of around 15. Okay, so the tip velocity is 15 times that of the wind velocity. At this, the efficiency hits around 0.45. Okay, then it starts to drop off. Okay, so why does this happen? At low speeds, the wind blade is too slow to interact with all the wind that is flowing through its area of rotation. Okay, so by the time the wind reaches this blade reaches this point, a lot of wind has escaped its area of influence. So there is not enough coverage. At very high speed tip velocities, the blade is so fast that turbulence induced drag effects and frictional losses become too much to overcome, and those impact the efficiencies. Okay, so there is an optimum sweet point depending on the number of blades you have for an optimum tip speed value at which the efficiency will peak. And this value peaks for a single bladed wind turbine at around 0.45, which is significantly lower than the Betz limit of 0.59. Notice that. And this happens at a very high tip velocity of 15. Okay. For a two-bladed wind turbine, because you have two blades, the coverage is more. So each blade has to cover only 180 degrees instead of 360 degrees. So you can have a lower tip velocity at which the efficiency peaks, and it peaks around a tip speed ratio of 11, and the efficiency is around 0.48. Okay, A three-bladed wind turbine had a tip speed ratio of 8. So the tip speed is 8 times the wind velocity, and its efficiency is also highest among all possible wind turbines, and it reaches around 0.5. Okay, so what is the case here is that your a three-bladed wind turbine has the highest efficiency and also has a reasonable tip velocity, so that its angular velocity omega is not too large that it puts unbearable strain on its rotary bearings. Okay, so that is why a three-bladed wind turbine is preferred over other variants. There are other types of wind turbines also. So for example, a Dutch mill has a four-bladed wind turbine. Okay, you can see its tip speed decreases very sharply to below 0.28. Okay, a Darius is a kind of a vertical axis wind turbine. We will not discuss that too much here because these are not usually used. Its tip speed ratio is around 0.45 and its efficiency is around 0.4. Okay, but these have lower efficiencies, older designs, so these are not usually used nowadays. Okay, so this is the preferred design that is used. Now the next question comes of what is the design of these wind blades. Okay, and here a lot of innovation has happened over the last few decades. Originally the wind blades were basically solid aluminium shapes. So basically the entire wind blade was made of solid metal, okay, which was very heavy and put a lot of load on the wind turbine hub with which it is connected. Okay, and this weight would create unbearable strains. So the wind blades had to rotate at a slower pace and it cannot be very high diameter. So basically a wind blade is like a cantilever. The higher the weight is, greater is the stress across the cantilever beam, correct? So this basic idea kind of gives you that heavier the wind blade, the shorter has to be its diameter so that the flexion and the torsional stresses are lower. Okay. So recently all of the wind turbine blade material have changed dramatically. So this is kind of how the blade is structured nowadays. So it's entirely hollow. Okay, there is an outer shell. Okay, then there is an infusion core and there is a spur, all of which is basically made of carbon fibers, primarily carbon fibers, sandwich foam, PVC, glass, etc. Okay, so modern materials, so if you look at the cross section, firstly it has aerofoil structure. So the structure of the wind turbine blades is very similar to structure of aircraft wings. Okay, it has an aerofoil shape to maximize the lift force that this wind turbine can generate. It is the lift force that is actually driving the wind turbine to rotate. Okay, so it has aerofoil shape. It's internally hollow. Okay, and is made of PVC, glass and carbon fiber laminates. Okay, and this kind of a structure, strut kind of things exist within the blade to give it stability. Okay, so this conversion to modern materials, okay, has made the wind turbine blades extremely lightweight and strong. Okay, and that is what has made it possible to have such large diameter wind turbine spans. Now, why do we use aerofoils? Okay, aerofoils primarily generate lift. Okay, basically a lift force is a force which acts on an aerofoil blade perpendicular to the direction of the flowing fluid. Okay, and this is because of a pressure imbalance that is caused between the upper contour of the aerofoil and the lower contour of the aerofoil. Basically, the wind or the fluid is accelerated over the upper contour and is decelerated over the lower contour. Okay, so the upper surface fluid accelerates, it decelerates over the lower surface. An accelerating fluid means its static pressure decreases. Remember Bernoulli's equation, P equals to half rho v square. Okay, so if V is increasing, P equals to half rho v square is constant. So if V is increasing, P must decrease. And here V is decreasing, so P must increase. So this lower contoured surface experiences a higher pressure and the upper contoured surface experiences a lower pressure. So there is a net upward force across the contour which creates the lift. Okay, and this we can see in a YouTube video which I will look into now. So this is a video of the flow over aerofoil shapes. So this is the, firstly, basically this is a flow over an aerofoil shape, and they have used smokes to show the streamlines around that aerofoil. Okay, so you can see the streamlines distorting around the aerofoil shape here. Okay. Now they are using high-speed camera to show the flow structure. You see the streamlines here more or less equally situated. Here it's decelerating. Now it is moving over the aerofoil. You can see the upper surface, the streamlines have increased. Lower surface streamlines are lagging. So these velocities are higher than these velocities. So that shows the flow acceleration to the top surface and the flow deceleration through the bottom surface. Now this angle of attack is basically the angle this chord line makes with respect to the wind direction. Okay, so there is a optimal set of angle of attacks where the lift force is maximized, and beyond that we have the effect of stall when the lift force basically decreases. Okay, until it becomes zero. So here you see the stall effect coming into the picture. Okay, so now the wind direction has stalled, and there is a sudden loss of lift because of this drag effect that is coming out. Okay, so the flow basically separates out of the aerofoil structure. It's no longer is hitting the surface completely. Its attached flow is getting detached suddenly. So you see this detachment happening, and that causes a rapid loss of lift. So in this detached mode, the cross sections on both sides are relatively same. Only if the flow is flowing through the contour, you have a higher cross section here and a deceleration. Okay, this is no longer happening, and so there is a sudden loss of the lift force. Okay, so there is a optimum angle of attack around this point, around 8, 10, 12 degrees, beyond which the lift force stops. So here basically this idea has been shown that you have a flow wind velocity in this direction. This is your wind turbine blade, right? And its cross section is oriented along this line angle. So this is the chord line of the turbine turbine cross section, and this velocity makes an angle. This angle is the angle of attack. Okay, and the lift force is perpendicular to the oncoming wind velocity. All right, and this is the distance d. Okay, so the lift force delta F is a lift coefficient, okay, which depends on this angle of attack phi between the velocity and the chord line. Okay, you can see the lift coefficient is given here. All right, so it kind of maximizes at 12 degrees and 16 degrees and then suddenly stalls. Otherwise, the lift force is increasing. Then this is rho v1 square by 2. This is the velocity of the oncoming wind with respect to the blade, rho v1 square by 2, into this cross sectional, this length, the chord length xb, into delta L, the length, the differential length of this cross sectional area. All right, note that your xb is varying from the base of your wind turbine to the tip where xb goes to 0. Okay, so xb is variable along this direction. Okay. So this delta L is basically a differential length. Okay, and we have to integrate this thing over the entire length of your turbine blade to get the total lift force that this blade is experiencing. All right, so let's kind of quickly discuss this once. So let's draw the diagram, the velocity diagram for a typical wind aerofoil structure. Let me be a bit careful here. Okay. Now here, this is your chord line. The effective velocity, let's say this effective velocity goes like this. So this is your effective velocity. So this is the velocity of the wind with respect to the moving blade. Remember, the blade for a turbine is actually rotating. Okay. So what is the velocity of wind with respect to the blade itself? That is your effective velocity. Okay. So this is your effective velocity. This is the v wind or v. Okay, this is the velocity of the wind in stationary coordinates at the blade cross section. That half rho a v square, that v is this one, v wind. Okay, and this is the v rotation. The rotational velocity, the tangential velocity at which this blade is moving. Okay, so if you see this, the blade is moving like this, right? So the velocity of the blade is like this, and the oncoming wind is like this. So always the rotational velocity is perpendicular to the wind velocity. Okay, so the aerofoil is cross section is like this. Here is circular. Of course, in case for your aerofoil, for this plane it's circular. For an aerofoil it will be this kind of a leaf shape. Okay, and the leaf shape will be slightly oriented like this. Okay, so we are looking, so if you in this figure, the length of the blade is actually perpendicular to the piece of paper. Okay, so the blade is like this, the wind is coming like this, the blade is moving up like this. All right, and so the rotational velocity is like this, the wind velocity is like this, the vector triangle creates the effective velocity like this. Okay, so that's one point. And then also the lift force is always perpendicular to the effective velocity. The velocity of the wind with respect to the blade, that direction and the lift force direction are perpendicular to each other. So FL is like this, this is 90 degrees, and this one too is 90 degrees. Okay, and what is the angle of attack? The angle of attack phi is this one, chord angle and the effective velocity of the wind. Okay, so that's the angle of attack. And this angle, the angle that the wind velocity in the stationary frame of reference and the effective wind velocity with respect to a blade, these two is called beta. Angle is beta. Another important angle is the angle that the blade chord makes with the rotational rotational velocity of the blade, the rotational velocity. This angle is called theta. Okay, so the velocity of the blade and the pitch angle, the angle between these and the chord, this is the chord length, is theta. Okay, so let's just this is your chord line. Okay, so now we can define each of these things. Okay. Phi is called angle of attack or blade angle. This is the angle between chord line and effective velocity of wind with respect to the blade. Okay. Theta is the pitch angle. It is the angle between the rotational velocity of the blade and the chord line. Okay, and beta is the angle between the wind velocity at blade with respect to ground and effective wind velocity with respect to blade. Okay, and remember what these three things are. This is the rotational velocity of the blade, the tangential velocity at which this blade cross section is moving. This is the wind velocity with respect to ground, and this is the effective velocity. Okay, so because it's a right triangle, V effective equal to whole square is V wind square plus V rotation square. Okay, or you can write also that V effective cos beta is V wind and V effective sin beta is V rotation. Okay, so V wind is V effective cos beta and V rotation is V effective sin beta. Okay, this is a right triangle. Another thing to note here, this is beta, so this is 90 minus beta. So this is 90 minus beta, this is phi, and this angle is theta. So theta plus phi plus 90 minus beta it also makes an angle equal to 180 degrees. Okay, so you can have this expression also, that theta plus phi plus 90 minus beta equals to 180 degrees. So this means theta plus phi is equals to 90 plus beta. Okay, you can get this relation as well. All right, basically this angle. Okay, you can see that. So this kind of gives you the idea of how these things are related to each other. All right, another important point is V rotation is equals to R into omega, where omega is in radians per second, is the angular velocity of your turbine. Okay, so this is the rotational velocity. All right, you know what the V wind is, and then if you know what your angles beta r, then you can evaluate the effective velocity at this blade cross section. Okay, and based on that effective velocity, then you can find your lift force values. All right. So your lift force then becomes delta F lift equals to C lift, okay, into rho V effective square by 2 into XB into delta L, where XB is the chord line length, okay, and this is the differential chord thickness. Okay, so this is where your effective velocity comes into the picture, and C lift, remember, is a function of phi, this angle of attack or blade angle. All right. Okay, so with that information, we will do a brief tutorial in the next class to show you how this example can work out. So for now, let's continue our lectures and see some other aspects of wind turbine.